Hello students, welcome back to the online session on basic electronics. Today we'll be learning about rectifiers, and in rectifier as particular we'll be studying about half-wave rectifiers. So let's see what contents we'll be learning today. First we'll be learning what is rectifier, that is the introduction to rectifier and half-wave rectifier in particular, and construction on working on half-wave rectifier, derivation for certain parameters, say VDC, DC voltage, TC current, RMS voltage, RMS current, rectifier efficiency, ripple factor, peak inverse voltage, and we'll solve certain problems related to half-wave rectifier, and then we'll discuss about the drawbacks in half-wave rectifiers. Okay, so let's start. So what is a rectifier? A rectifier is an electrical device that converts an electrical alternating current, that is AC, into a direct current DC by using one or more PN junction diodes. So this is the definition of rectifier theoretically. So it is an electrical device that converts an alternating current into direct current, that is conversion of AC into DC. Okay, so the rectifiers are mainly classified into two types: half wave rectifier and full wave rectifier. Okay, so in this session we'll be concentrating only on half wave rectifier. So half wave rectifier use one diode, while a full wave rectifier use multiple diodes. Okay, so this is theoretical introduction. Before that, you should know what is this alternating current or direct current, okay, and what are semiconductor diodes. So already in the previous session I have given you introduction about diodes and how it is represented, what is the working of diode, everything is covered. Okay, I hope you have gone through that video. Okay, before introducing to rectifier, I want you to learn few concepts. Okay, so
we must
look at this
know
video.
three things. Number 1, alternating voltage and current. Number 2, direct voltage and current. Number 3, semiconductor diode. Let's discuss these three things one by one. Alternating voltage and current. When available voltage from an electrical source changes its direction periodically, the voltage is known as alternating voltage, and the source from which it is available is known as AC source. If we plot waveform of this voltage by drawing magnitude of voltage on y-axis with respect to time on x-axis, we will find that the waveform is sinusoidal in nature, which shows that voltage increases in one direction, achieve positive maximum amplitude, decrease to 0, then it changes its polarity, achieve negative maximum amplitude, and again reduced to 0. Now, if we apply this alternating voltage to an electric load, alternating current gets set up in the circuit. Flow of current follows the nature of applied voltage. This changing current is known as alternating current. Direct voltage and current. When available voltage and current does not changes its direction with respect to time, then it is known as direct voltage and current respectively. For example, potential difference, or we can say voltage available at terminals of a battery or a cell, is direct voltage because it does not alter its polarity and remain constant in magnitude when time proceeds. Consequently, when we apply this voltage across an electric load, current will also direct in nature, means It does not change its direction and magnitude with respect to time. Semiconductor diode. It is an electronic two-terminal device. The two terminals called as anode and cathode. This device has a special property that it only conducts electricity when it is forward biased. Forward biased means when anode is at higher potential or positive polarity and cathode is at lower potential or negative polarity. In this case, the diode offers very low resistance to a circuit.
Okay, so this is the three concept you have understood. So now by now you have understood what is actually a AC voltage and DC voltage or current. Okay, so alternating current, that is, it is periodically changing its polarity. Okay, that is alternating, whereas indirect doesn't change its polarity with respect to time. Now let us see half wave rectifier. Half wave rectifier allows only one half cycle, that is positive half cycle of the AC voltage through it, and will block the other half cycle, that is negative half cycle of AC voltage as shown in the figure. So here you can see it is a sinusoidal signal with both positive and negative cycles. Okay, and here the output is just only the positive half cycle, whereas the negative half cycle is blocked or it doesn't appear, right? So it becomes almost a pulsating DC current. So from alternating current, it has become a pulsating DC current. Okay. So let us see now the construction and working of half wave rectifier. Okay, so the circuit diagram of half wave rectifier uses a diode and a step down transformer as below. So here you can see the circuit diagram. Okay, this is called a step down transformer. We are using only one diode here, D1, then the resistance, load resistance RL. Okay, the input voltage, that is the AC input voltage, is given across the step down transformer. So now you should understand how the step down transformer work. What is this? Okay, so before going into how the working exactly of the diode and half wave rectifier, first let us get to know what is the step down transformer. Okay, so step down transformer looks like this. Okay, so step down transformer, there is an input where AC supply is given and there is a primary winding. So this is an iron core. To that coils are turned. Okay, so here it is the primary winding and this is the secondary winding. Again the coils are turned. Okay, so there are two types of transformers, step up and step down transformer. So to understand this better, just look at this video.
Connected to an AC input voltage and is called the primary coil. The other coil is connected to an output circuit with a load resistance and is called the secondary coil. The two coils are well insulated from each other and do not form a physical electrical connection. This gives the transformer its unique electricity altering properties. Transformers can either step up or step down a voltage. In a step-down transformer, the number of turns in the primary coil is greater than the number of turns in the secondary coil. In a step-up transformer, the number of turns in the secondary coil is greater than the number of turns in the primary coil. The constantly changing current driven by an alternating voltage source induces a changing magnetic field in the core of the transformer. The magnetic field created by the alternating current in the primary coil generates the flux in the transformer core. The secondary coil converts the flux back into current flow and produces a voltage at the load or resistance in the secondary circuit. If there are fewer coil turns on the secondary than on the primary, this is called a step-down transformer. The resulting voltage in the secondary circuit will be less than the primary. In this example, we have 20 turns on the primary coil and 10 turns on the secondary coil. To determine the decrease in voltage occurring in this step-down transformer, we can use a simple ratio formula. This formula simply states that the secondary voltage to primary voltage ratio is the same as the secondary coil to primary coil turn ratio. Rearranging the formula and then dividing 10 turns by 20 turns, we get 0.5 multiplied by 120V. This results in a calculated step-down voltage of 60 volts.
Okay, so now you have understood how the step-down transformer work. So now the understanding is simpler for you. So you have understood that we are giving a AC supply. So from the power supply, 230 volts or 220 volts, and that is stepped down using the step-down transformer. That is, the voltage is reduced here, and depending on that, it is made to work. Okay, so how is the primary and secondary windings, how does it work? I have clearly given in that video. Okay, so now let us see a half-wave rectifier animated video. You all know that the diode conducts only in one direction. When is it? When the anode side, that is the P side, will be connected to the positive terminal of the battery, and N side is connected to the negative terminal of the battery. That is, it offers low resistance and it allows the conduction of current. Now when we reverse bias it, that is when the P side is connected to the negative terminal of the battery and N side is connected to the positive terminal, what happens? High resistance is provided, or the diode is in off state. Okay, so here for better understanding, I will just say diode is in on state or off state depending on the input that what we are giving. So input is obviously a AC signal, or that is a sinusoidal signal, as you see here. Okay, so a sinusoidal signal has a positive half cycle as well as negative half cycle. So I can say positive in the sense it is positive supply given at that point. And when it is in the negative half cycle, it is tending towards the negative side. Okay, so now see in the circuit. Okay, so we are giving a positive half cycle. What happens when you are giving the positive half cycle is the diode becomes forward biased and it is in on state, as you see here, and the current will flow across the load. What happens when you are giving the diode, the input in the negative half cycle? The diode is reverse biased now, so it will not allow the flow of current. See, now this is the negative side. Now the diode will not, it will stop this flow of current, it will block, it will offer high resistance, so the output is 0. Okay, hope this is clear for you. So let us see. The step-down transformer is used to reduce the AC supply voltage to the required level. Okay, so step down. So you're reducing the voltage to your required level. The AC voltage to be rectified is applied across the primary of the transformer, and the voltage across the secondary of the transformer is available for rectification. Okay. Half-wave rectifier rectifies only one half cycle of the AC input. Okay, now let the voltage applied across the primary of the transformer be V1 equal to Vm sin omega t. Okay, so this is the sinusoidal signal. We are writing it in the form V1 is equal to Vm sin omega t, where Vm is the peak value. Okay, and omega is the phase. Omega t is the phase. Okay, now let us see. We have already studied what is the step down transformer doing. Depending on the number of turns, if the primary turns is higher than the secondary, then it is working as a step down transformer. So in that video it was very clear. Okay, so in that the ratio, that is the voltage across the secondary of the transformer available for rectification is given by, so it is nothing but Vs divided by Vp is equal to N2 by N1. That is, the voltage across secondary to the voltage across primary is equal to number of turns in the secondary to number of turns in the primary. That can be solved or written in this form, that is V2 is equal to N2 by N1 into Vm sin omega t, where V2 is the voltage across the secondary, N2 is the number of turns in the secondary, N1 is the number of turns in the primary coil, and Vm is the peak value, Vm sin omega t is the input voltage across the primary. Okay, so it is very clear given here. So if the number of turns is equal, then what will be our V2, that secondary voltage? V2 is equal to Vm sin omega t. Always remember, this secondary voltage is available for rectification, or this secondary voltage is what given as the input for the diode. Okay, so what is the input voltage across the diode? If we see, V2 is equal to Vm sin omega t. Okay, be very clear, students. So V2 is equal to Vm sin omega t will happen only when N2 is equal to N1. Otherwise, this is your voltage equation. Okay, so input voltage V2 is equal to N2 by N1 into V1 also you can write. Instead of Vm sin omega t, you can write V1. V1 is nothing but voltage across the primary, or Vm sin omega t. Okay, now let us see how it worked. Okay, so during the positive half cycle, okay, 0 to pi, okay, we got the output, right? Okay, so now I am plotting the graph, okay, across, that is the Vm versus time. Okay, the voltage across the voltage, input voltage V with respect to time. Here I am plotting the current, output current with respect to time, and here I am plotting output voltage with respect to time. Okay, so this is input, these two are outputs, that is output current and output voltage. Okay, let us see now when we are giving input voltage, that is during the positive half cycle. Yes, the output also we got the output as positive half cycle. Yes, because the diode afford low resistance, and whatever the current was it produced to the load. But during the negative half cycle, diode became off, so no current produced or no voltage produced, right? And during the next positive half cycle, this is periodic, so again the positive half cycle, the current is produced, and during the negative half cycle it is 0. Okay, so from 0 to pi there is output voltage or current, but from pi to 2 pi it is 0. Again it occurs periodically. 2 pi to 3 pi it is there is input voltage which is given across the load, but during 3 pi to 4 pi it is 0. This graph is very important with respect to examination point of view. You have to clearly mention all the values. Okay, so here this Vm is the peak value of the input voltage. Here Im is the peak current value. Okay, and here the Vm is the peak output voltage value. Okay, and this average, that is average value, is taken as IDC, and here it is taken as VDC. Okay, everywhere you are plotting the graph with respect to time. Okay, so clearly you need to mention all these factors when you draw the graph. Okay, so during the positive half cycle, very clear explanation for this, that is the working of half wave rectifier. During the positive half cycle, the diode conducts and the current I0 flows through the load. The load voltage V0 is equal to I0 into RL. During the negative half cycle, the diode gets reverse biased and the current I0 is 0. Correct? The voltage V0 equal to 0. So this is the two condition. This is for the positive half cycle and this is for the negative half cycle. Hope this is clear for you. Now, from the circuit shown in the figure, okay, so we know that I0 is equal to V2 divided by RF plus RL. According to Ohm's law, V is equal to IR. Here we have RF and RL, right? So this is the forward resistance, and this is the load resistance. Okay, so diode has a forward resistance with it. Okay, so when we consider, it is very negligible, but if we consider that it as RF, okay, and load resistance is RL. Clear? Okay, so now if we write in that equation, I0 is equal to V2. V2 is what? V2 is the input voltage which is given to the diode. Okay, and RF plus RL is the total resistance. Or I0 we can write, if you substitute, what is V2? V2 is nothing but Vm sin omega t divided by RF plus RL. Or I0 can also be written as Im sin omega t, where Im is equal to Vm divided by RF plus RL. This is the peak load current. Hope this equation is clear for you. So I naught is equal to Im sin omega t, where Im equal to Vm divided by Rf plus RL is the peak load current. Now first let us derive the parameters. First is average DC load current. How to find average DC load current is, you have to use IDC is equal to area under one cycle of I naught divided by period of I naught. For this we need to look onto the graph. Okay, so in this graph you have to check from 0 to 2 pi what we have to write. Okay, so this is period of one full cycle, right? So if I take the period, it is 0 to 2 pi. Okay, so how should I write that? Area under one cycle of I naught divided by period of I naught is nothing but one full cycle is the integration from 0 to 2 pi I naught d omega t divided by period of I naught is 2 pi. Okay, substituting what is I naught, we get IDC is equal to 0 to 2 pi Im sin omega t d omega t divided by 2 pi. Now we will split this because we know that from 0 to pi we have value, but from pi to 2 pi the value is 0. So when I split this and write 1 by 2 pi, I can take it outside, then it will be 0 to pi Im sin omega t d omega t plus pi to 2 pi 0 into d omega t. Okay, so 0 will remain, will cancel or it becomes 0. Here IDC is equal to Im by 2 pi. Im will take out. Integration of 0 to pi sin omega t will be minus cos omega t with limit 0 to pi. When we substitute the limits cos pi minus cos 0, take a minus outside, then we'll get reduced equation IDC is equal to Im by pi. Okay, so it will be Im by 2 pi into 2 as such, so it will become Im by pi. Okay, so this is the parameter you find for DC load current for half wave rectifier. Very clear. IDC is equal to Im by pi, where Im is the peak value. Now let us find average DC voltage. To find average DC voltage, we know the Ohm's law, VDC is equal to IDC into RL. IDC we have just found out. What is the value? Im by pi into RL. VDC can be written, if I take 1 by pi outside and write Im with respect to Vm, then it will become Im is nothing but Vm divided by Rf plus RL into RL. Okay, if I take Vm by pi as common, then it will be RL divided by Rf plus RL. Or VDC equal to Vm by pi divided by Rf plus RL divided by RL. When it goes up, it will become Vm by pi divided by 1 plus Rf by RL. So this is the equation for average DC voltage. Okay, for our average DC voltage, you need to write this equation. Hope this is clear. Okay. Next, let us find how to derive the parameter for RMS load current. To find RMS load current, you have to use this equation. IRMS is equal to square root of area under one cycle of I naught square. Very important. See here, it is I naught square divided by period of I naught. So same way how I have written for DC current, I will use the same way. IRMS is nothing but square root of integration 0 to 2 pi I naught square, because it is I naught square, into d omega t divided by 2 pi. Or IRMS, if I split this and if I substitute what is I naught is nothing but Im sin omega t, or I naught square is equal to Im square sin square omega t d omega t plus integration pi to 2 pi 0 d omega t. When I substitute the values, or when I go for integration, then I get this reduced to Im into root of 1 by 4 pi integration d omega t minus integration of 0 to pi cos 2 omega t d omega t. Okay, all of you know integration. Integration of 0 to pi d omega t is nothing but omega t with limit 0 to pi. Integration of 0 to pi cos 2 omega t is sin 2 omega t by 2 with limit 0 to pi. After you substitute the limit values, you will get the reduced equation where the IRMS is equal to Im by 2. Hope this is clear for you how to find RMS load current. Next, let us find RMS load voltage. RMS load voltage by the same equation, that is using Ohm's law, Vrms is equal to IRMS into RL. VRMS is IRMS is nothing but what we got just now, Im by 2 into RL, or VRMS is equal to 1 by 2 into Vm divided by Rf plus RL into RL, or VRMS is equal to Vm by 2 divided by 1 plus Rf by RL. This is the RMS load voltage for half wave rectifier. Now let us find the rectifier efficiency. As the name indicates, rectifier efficiency is the ratio of the DC output power to the AC input power supplied to the rectifier. Rectifier efficiency means how efficient it is able to convert the AC power, input power, to DC output power. How it is able to convert, how well it is efficient, it is converting AC input to DC. Okay, that is called as rectifier efficiency. Or with respect to formula, it is written as PDC divided by PI, where PDC is the DC output power and PI is the AC input power. Now, how do we find this? DC output power is given by PDC is equal to I square DC into RL. Everyone know this equation. Power P is equal to I square R, or PDC is equal to I square DC into RL. For half wave rectifier, IDC is given by IDC is equal to Im by pi, because we have found that equation. Okay. Therefore, DC output power can be expressed as PDC is equal to Im square by pi square into RL, substituting the value of IDC in PDC. AC input power is given as Pi is equal to I square RMS into RF plus RL. For half wave rectifier, IRMS is given by IRMS is equal to Im by 2, which we have derived, right? Now substituting this, we can express the efficiency as Im square divided by pi square into RL divided by Im square by 4 into RF plus RL. Now when I substitute this, I will get the reduced equation 0.406 divided by 1 plus RF by RL. Okay, that is 40.6 divided by 1 plus RF by RL in terms of percentage. But if the diode is idle, RF is taken as 0. Right? So if you substitute that, then percentage rectifier efficiency is given as 40.6. So you have understood now how efficient is the rectification. It is 40.6%. Whatever the AC input power, its 40.6% is converted. Okay. Now, next let us find what is ripple factor. It is the ratio of RMS value of AC component present in the rectified output to the DC component of the rectified output. Okay, that is given by VAC divided by VDC. Okay, so this is ripple factor is what ripples are present in the output. How much amount of ripples are present in the output. Okay, that is ripple factor. To find that, we have the ripple factor, or in formula we write as VAC divided by VDC. That is VAC is the voltage, AC voltage divided by DC voltage. How do we find this? The output of the rectifier is a pulsating DC and has two components, that is AC component of RMS value VAC and DC component VDC. Here the output of the rectifier, if you have noted, is not direct pure DC but it is pulsating DC. Since it is pulsating DC, it has two components, that is AC component of RMS value which is called as VAC and DC component VDC. We know that the total power output is a sum of power of DC and AC components. That is total RMS value of rectified output square is equal to DC value square plus RMS value of AC component square. So this equation V square RMS is equal to V square DC plus V square AC is very important. Okay, so when we write this particular equation, V square RMS by VD square is equal to 1 plus VAC by VD square. For this equation, what we are doing is we are dividing both sides by VDC square. So when we write this, we know that VAC by VDC is nothing but ripple factor. Okay, so RMS square divided by VDC, the whole square is equal to 1 plus eta. or it can be written as root of Vrms divided by Vdc whole square minus 1. Okay, when you substitute Vrms we know that Vm by 2 divided by 1 plus Rf by RL, and Vdc we know that Vm by pi divided by 1 plus Rf by RL. That is both this equation we have derived recently. Okay. Therefore, substituting that value, we will get a reduced equation as like this: root of pi by 2 the whole square minus 1, that is 1.21. Okay, so the ripple factor is 1.21, or VAC is equal to 1.21 DC. Therefore, in the half wave rectifier, the AC or the ripple content or component is 121% of the DC component. Hence, half wave rectifier is not recommended for practical applications. So, you have understood that VAC is 1.21 times the VDC. If you multiply by, in terms of percentage by 100, then it is 121% of AC component is present in this. Then it is obviously it is not recommended for practical application, that because so much AC component is present in that particular pulsating DC, then it is not at all rectified. Okay, now let us see how to find peak inverse voltage. Peak inverse voltage is the maximum reverse voltage that can be applied for the diode. You know that when the diode is reverse biased, then the diode is in off state. Okay, how much reverse voltage you can apply for that diode is called peak inverse voltage. That diode can withstand is called peak inverse voltage. So I am giving here negative, minus given to the diode. Obviously diode is in off state. So that is called as reverse voltage VR. Now we need to find how much it can withstand to that. Okay, and I naught is also 0. Okay, to find that we will apply KVL here. KVL application, that is V2 minus VR minus V2 minus VR plus V0 into RL, or I0 into RL is equal to 0. Okay, so V2 minus VR plus I0 into RL equal to 0. Since I0 equal to 0, we will get the reverse voltage VR is equal to V2, or that is equal to Vm sin omega t. So the peak inverse voltage, this reverse voltage it can withstand is Vr max, that is equal to Vm when sin omega t equal to 1. So peak inverse voltage is Vm for half wave rectifier. So all the derivations we have covered. Okay, now let us solve problems on half wave rectifier. Okay, so first problem is a sinusoidal voltage of peak value 40 volts and frequency 50 Hz is applied to a half wave rectifier having a load resistor of 800 ohm and RF of the diode is 8 ohm. Calculate all these parameters. First, you have to note down when you get a problem is what are the given parameters. Here the given parameter is a sinusoidal voltage of peak value. So Vm we have got as 40 volts. Frequency F is 50 Hz. And load resistor value RL is 800 ohm. Forward resistance RF is 8 ohm. Okay, so these are the given parameters. Now let us solve this step by step. Okay, so first peak current. How to find peak current? Peak current is given by Im is equal to Vm divided by Rf plus RL. Vm is 40, Rf is 8, RL is 800. Substitute it, you will get the answer. DC current is given by Im by pi. Substituting the value of Im, which I have got this, we will get 15.75 milliampere. RMS current is equal to Im by 2 for half wave rectifier. So it is 49.5 milli divided by 2. So that is equal to 24.75 milliampere. DC output power is given by PDC is equal to I square DC into RL. So substituting that, we will get 198.45 milliwatt. AC input power is given by PI is equal to I square RMS into RF plus RL. So substituting that, we will get PI is equal to 494.95 milliwatt. Okay. So this is half we have found all the parameters. Now what is left out? Rectifier efficiency. How to find rectifier efficiency? It is given by the equation PDC divided by PI into 100%. PDC is 198.45 milliwatt and PI is 494.95 milliwatt. So when you substitute that, you will get 40.09%, because you know half wave rectifier will give only so much. Okay, so you should relate this. Okay, so it will be around 40.09%. Let us solve one more problem. The input to a half wave rectifier is given through a 10:1 transformer from a supply of 230 sin 314T. If RF is 50 ohm and RL is 500 ohm, determine the following parameters. Here, let us write the given parameters. So, given, here the turn ratio is given. That is, N1 is to N2 ratio is given. N1 is given as 10 and N2 is given as 1. 10 is to 1. Supply to the secondary transformer is given as 230 sin 314T. RF forward resistance is given as 50 ohm. Load resistance is given as 500 ohm. Now we are supposed to find DC load voltage, RMS load voltage, peak inverse voltage, rectifier efficiency, DC power delivered to load, frequency of output waveform. How will we find the frequency of output waveform? Here this equation is nothing but the voltage, input voltage across the primary. Okay, because it is given directly from a supply. So secondary voltage is given by V2 is equal to N2 divided by N1 Vm sin omega t. That is 1 by 10 into 230 sin 314T. So secondary voltage is equal to 23 sin 314T. Okay. So here from a supply means the input is given to the primary. This is the primary voltage. We need to find what is the voltage given to the diode, that is the secondary voltage. To find that, we know the equation V2 is equal to N2 by N1 into Vm sin omega t. So directly substitute that Vm sin omega t is nothing but V1 or Vp. Okay, substituting that we will get V2 as so much value. Now from this we can find frequency directly. Omega is nothing, omega is equal to 2 pi f, or f is equal to omega by 2 pi. Substituting that we will get 50 Hz. Now let us find DC load voltage. We know that the equation is Vm divided by pi divided by 1 plus Rf by RL. So you will get this as 6.66 volts. RMS load voltage is Vm by 2 divided by 1 plus Rf by RL. So you will get this as 10.45 volts. Peak inverse voltage across the diode is given by Vm. That is, Vm is already we have got here. What is Vm? Vm is 23. So 23. DC output power is V square DC by RL. VDC we have already got 6.66 divided by 500. PDC is equal to 88 milliwatt. Rectifier efficiency is 40.6 divided by 1 plus RF by RL. RF is 50 and RL is 100. Substituting that we will get 36.91. Okay, this is one more kind of problem where the turns ratio will be given and the primary voltage is given. The previous one we have solved is directly they have given the secondary voltage with no turns. Now what is the disadvantage of half wave rectifier is? Obviously we have seen the ripple content is 121%, means the output contains AC components frequency is equal to the supply frequency. So much filtering is needed. We have to use filters. Next drawback is the AC supply delivers power during half cycle only, so output is low. Only during the positive half cycle we get the output, so the output is low. That is the main two disadvantage of half wave rectifier. I hope half wave rectifier session is clear for you. All the derivation you need to work down and the problems you need to solve, then only you will understand how this is working. So if you want to know more about this, you can click on the below links. Thank you.